Have you ever stared at the night sky and felt blown away by how little we actually understand about it? We're living on a tiny planet spinning through endless space, and most of us rarely stop to think about just how strange and unbelievable the universe really is. Get ready, because tonight we're diving into ideas that will flip your understanding of reality upside down. And I promise you, by the end of this video, you'll never look at the stars the same way again. Make sure you watch it till the very end. Feel free to let me know in the comments where you're watching from tonight. Are you under a clear night sky or somewhere cloudy tonight? So settle in, close your eyes if you'd like, and prepare to be amazed by some of the most breathtaking facts about our universe. Facts so extraordinary, they might just change how you see everything around you. Let's begin our cosmic meditation with something that will make you reconsider the very nature of emptiness itself. You see, when we look up at the night sky, we often think of space as this vast, empty void punctuated by distant points of light. But here's something that might surprise you. Space isn't empty at all. In fact, what we call empty space is one of the most active, energetic places in the entire universe. Every cubic centimeter of seemingly vacant space contains what physicists call quantum fields. These aren't science fiction concepts, they're fundamental features of reality itself. Imagine space as an ocean, and we're like fish who've never noticed the water we swim in. These quantum fields are constantly fluctuating, creating pairs of particles that pop into existence for the briefest instant before annihilating each other and disappearing back into the void. This phenomenon, known as vacuum fluctuations, means that even in the darkest, most isolated regions between galaxies, space itself is alive with activity. Particles are being born and dying in time frames so brief they exist for less than the time it takes light to cross the width of a proton. It's as if reality itself is gently breathing, expanding and contracting at scales so tiny we can't perceive them directly. What makes this even more remarkable is that these quantum fluctuations aren't just theoretical curiosities. They have measurable effects on the world around us. They contribute to something called the Casimir effect, where two metal plates placed extremely close together in a vacuum will actually be pushed toward each other by the pressure of virtual particles. They influence the behavior of atoms and the way light interacts with matter. In essence, the seemingly empty space around you is contributing to the very structure of reality. Think about this the next time you're sitting quietly in a room. The air between your hands, the space above your head, the gap between the pages of a book, all of it is teeming with invisible activity. Quantum fields are oscillating, virtual particles are dancing into and out of existence, and the fabric of space-time itself is gently vibrating like the surface of a pond disturbed by an invisible breeze. Moving outward from the quantum realm to something more tangible, let's explore one of the most beautiful and mysterious phenomena in our cosmic neighborhood, the aurora. Most people have seen photographs of these ethereal curtains of light dancing across polar skies. But the story behind their creation is even more magical than their appearance. The aurora begins its journey not on Earth, but on the surface of our Sun, 93 million miles away. Deep within the solar core, nuclear fusion reactions are constantly releasing tremendous amounts of energy. Some of this energy escapes as charged particles, primarily electrons and protons, that stream away from the Sun at speeds of up to 1 million miles per hour. This river of particles is called the solar wind, and it's constantly washing over our planet. Now, you might wonder why we're not constantly bombarded by this radiation. The answer lies in one of Earth's most protective features, our magnetic field. Generated by the motion of molten iron in our planet's core, this invisible shield deflects most of the solar wind around us, like water flowing around a stone in a stream. But here's where it gets interesting. Near the magnetic poles, some of these charged particles manage to slip through our magnetic defenses and dive down into our atmosphere. When they collide with oxygen and nitrogen molecules high above the surface, something wonderful happens. The impact energizes these atmospheric particles, causing them to release photons of light in specific colors. Oxygen glows green when struck at lower altitudes and red at higher altitudes. Nitrogen produces blue and purple hues. The result is those magnificent sheets of colored light that seem to dance across the sky like cosmic silk scarves caught in a celestial breeze. Each aurora is unique, shaped by the ever-changing interaction between our magnetic field and the solar wind. What's particularly enchanting is that this process connects us directly to the nuclear fires of our star. Every photon of aurora light you see began its journey in the sun's core, traveled millions of miles through space as a charged particle, navigated our planet's magnetic field, and finally manifested as visible light in our atmosphere. You're literally watching the sun paint pictures in our sky using Earth's magnetic field as a canvas. Yes. Let's drift now to contemplate something that challenges our everyday understanding of reality, the true nature of gravity. Most of us learned in school that gravity is a force that pulls objects toward each other. Massive things attract less massive things, which is why apples fall from trees and why we stay planted on the Earth's surface. But this intuitive understanding, while useful for daily life, only scratches the surface of gravity's true nature. Einstein's revolutionary insight was that gravity isn't really a force at all. Instead, it's the result of massive objects actually bending the fabric of space-time itself. Imagine space-time as a vast, flexible sheet stretched tight. Now picture placing a bowling ball in the center of this sheet. The ball's weight would create a depression, a curved region around it. If you then rolled marbles across the sheet, they wouldn't travel in straight lines anymore. They would follow the curves created by the bowling ball's presence. This is essentially what's happening throughout the universe. The sun creates a depression in space-time, and Earth follows the curved path around this depression, which we perceive as an orbit. We experience this curvature as gravity, but what's really happening is that we're following the straightest possible path through curved space-time. This insight leads to some truly mind-bending implications. Time itself flows differently in the presence of massive objects. The stronger the gravitational field, the slower time moves relative to areas with weaker gravity. This isn't just theoretical physics, it's measurable reality. Satellites in orbit experience time slightly faster than we do on Earth's surface because they're farther from our planet's gravitational influence. Even more extraordinary is the realization that gravity travels at the speed of light. If the sun were to suddenly vanish, we wouldn't feel the gravitational effects of its disappearance for about 8 minutes, the same time it takes sunlight to reach us. Gravity, like light, is information traveling through space-time, ripples in the cosmic fabric that carry news of changes in mass and energy. These gravitational waves were first detected directly in 2015, when scientists observed the ripples created by 2 black holes colliding over 1 billion years ago. The waves that reached Earth were so subtle they stretched and compressed space by less than 1/10,000th the width of a proton. yet we detected them, proving that space-time itself can vibrate like a cosmic drumhead. Now, let's venture into the realm of stellar evolution and discover how the universe creates the elements that make life possible. Every atom in your body, except for hydrogen, was forged in the nuclear furnace of a dying star. This isn't poetic metaphor, it's literal scientific truth. You are made of stellar debris, recycled cosmic material that has been on an incredible journey through space and time. In the beginning, the universe contained only the lightest elements, hydrogen and helium, with trace amounts of lithium. But inside the cores of massive stars, nuclear fusion creates tremendous pressure and heat, forcing lighter elements to combine into heavier ones. Carbon, oxygen, nitrogen, silicon, iron, all the elements essential for rocky planets and biological life, were manufactured in stellar cores over millions of years. The process is beautifully systematic. Stars spend most of their lives fusing hydrogen into helium in their cores. When the hydrogen runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. This process continues, creating successive layers of increasingly heavy elements, like an onion made of different nuclear fuels. But here's where stellar death becomes the universe's gift to future generations. When massive stars finally exhaust their nuclear fuel, they can no longer support themselves against gravity's relentless pull. The core collapses catastrophically, triggering a supernova explosion so powerful it can briefly outshine an entire galaxy containing hundreds of billions of stars. These stellar detonations don't just mark the end of a star's life, they're cosmic seed dispersers, scattering newly forged elements across vast regions of space. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar cores and distributed by supernova explosions billions of years ago. Even more remarkably, the heaviest elements, like gold and platinum, require even more extreme conditions to form. Many of these precious metals are created when neutron stars collide, events so violent they can be detected as gravitational waves across billions of light years. The gold in jewelry, the silver in electronics, even the rare earth elements in your smartphone all originated in some of the most powerful explosions in the universe. This cosmic recycling program has been operating for over 13 billion years, with each generation of stars building on the chemical legacy of their predecessors. Our Sun is at least a third-generation star, formed from gas clouds enriched by the deaths of earlier stellar generations. Without those ancient supernovas, there would be no rocky planets, no complex chemistry, no life as we know it. You are literally made of stardust, but not in some vague, metaphorical sense. The atoms that comprise your body have been on an epic journey through space, spending eons as part of interstellar gas clouds, condensing into new stars and planets, and eventually finding their way into the biological processes that created and sustain you. Every breath connects you to this vast cosmic story of stellar birth, death, and rebirth. As we continue our gentle drift through these cosmic revelations, let's pause to appreciate something truly extraordinary about our position in the universe. We exist at a unique moment in cosmic history, a brief window of time when the universe is just the right age and size for us to observe its deepest secrets. This cosmic perspective reveals how special our moment of existence really is. The universe is currently about 13.8 billion years old, which might seem like an incomprehensibly long time. But in cosmic terms, we're living during the universe's youth. Stars will continue forming and dying for trillions of years to come. Galaxies will merge and evolve. The cosmic web of dark matter will continue its slow, majestic dance across billions of light years. Yet we exist at the perfect time to witness the universe's childhood. We can still see the afterglow of the Big Bang in the cosmic microwave background radiation. We can observe galaxies as they appeared when the universe was only a fraction of its current age. We can study the first generation of stars and watch planetary systems forming around young suns. In the far future, expansion will carry distant galaxies beyond the reach of light. The cosmic microwave background will fade into undetectable whispers. Future civilizations, if they exist, will inhabit a much darker, emptier-looking cosmos, with no evidence of the Big Bang or the early universe's dramatic history. They might never discover that the universe had a beginning, or that it's filled with dark matter and dark energy. We are cosmically privileged observers, living at just the right moment to piece together the universe's origin story. The light from the most distant galaxies is just now reaching us, carrying information about cosmic dawn. We exist in the sweet spot between the universe being too young to have developed complex chemistry and life, and too old to preserve clear evidence of its exotic origins. This realization transforms our perspective on everything around us. The night sky isn't just beautiful, it's a cosmic library containing the history of everything that exists. Every photon that reaches your eyes has been traveling for years, decades, or even billions of years to deliver its message about distant suns and ancient epochs. When you gaze up at the constellation Orion on a clear winter evening, you're receiving light that left those stars at vastly different times. The light from Bellatrix began its journey about 250 years ago, when Mozart was composing his first symphonies. The glow from Betelgeuse started traveling toward Earth around the time the first humans were learning to control fire. Each point of light in that familiar pattern carries news from a different era of history, all arriving at your retina in the same moment. This temporal layering extends far beyond what our eyes can see. Radio telescopes can detect signals from galaxies so distant that their light began traveling when the universe was less than 1 billion years old. We're essentially time travelers, using electromagnetic radiation as our vehicle to peer into the cosmic past. Every observation is archaeology, every measurement a glimpse into what was rather than what is. Let's drift now towards something that might make you question the very ground beneath your feet. Our planet Earth, this solid, stable foundation we call home, is actually hurtling through space at speeds that would make any earthly vehicle seem glacially slow. Yet we feel none of this motion because we're all moving together, carried along by gravitational forces we barely notice. Right now, as you listen to these words, you're spinning with the Earth's rotation at roughly 1,000 miles per hour if you're near the equator. But that's just the beginning of our cosmic journey. Our entire planet is simultaneously racing around the Sun at about 67,000 miles per hour, covering the 584 million-mile circuit of our orbit in exactly 1 year. The Sun itself isn't stationary either. Our entire solar system is careening through the Milky Way galaxy at approximately 514,000 miles per hour, completing one galactic orbit every 225 million years. The last time we were in this same position relative to the galactic center, dinosaurs were just beginning to diversify across the supercontinent Pangaea. Even more remarkably, our galaxy is falling toward the Andromeda galaxy at roughly 250,000 miles per hour. In about 4.5 billion years, these two massive collections of stars will merge in a cosmic dance that will fundamentally reshape both galaxies. New star formation will be triggered, Existing solar systems will be flung into different orbits, and the night sky will be transformed beyond recognition. Yet despite all this motion through space and time, here you are, breathing calmly, perhaps settling deeper into your bed or chair, completely unaware of the tremendous velocities carrying you through the cosmos. It's a beautiful reminder that motion is always relative. We don't feel like we're moving because everything in our immediate environment shares our motion through space. This principle of relativity extends to some of the most profound discoveries in physics. Light always travels at the same speed relative to any observer, regardless of how fast that observer might be moving through space. This seemingly simple fact led Einstein to realize that time and space are not separate entities, but aspects of a unified space-time that can stretch and compress, depending on motion and gravity. Speaking of light, let's explore one of the most extraordinary properties of these electromagnetic waves that connect us to the cosmos. Light doesn't just travel through space, it carries information encoded in its wavelength, intensity, and polarization. By carefully analyzing starlight, astronomers can determine not just what distant objects are made of, but their temperature, motion, age, and even their magnetic field strength. This cosmic spectroscopy works because different elements absorb and emit light at very specific wavelengths. When astronomers spread starlight into a rainbow spectrum, they see dark lines where certain wavelengths have been absorbed by elements in the star's atmosphere. These spectral fingerprints are unique to each element, allowing us to identify the presence of hydrogen, helium, carbon, oxygen, and dozens of other elements in stars thousands of light years away. Even more remarkably, the wavelength of light shifts slightly when its source is moving toward or away from us. This Doppler effect, similar to how a passing ambulance's siren changes pitch, allows us to measure how fast stars and galaxies are moving. This technique revealed that the universe itself is expanding, with distant galaxies racing away from us at speeds proportional to their distance. The implications are staggering. Every photon of starlight contains a wealth of information about conditions in distant corners of the universe. We can determine that the same physical laws operating on Earth also govern the behavior of matter in galaxy clusters billions of light years away. The universe appears to be remarkably uniform in its fundamental properties, suggesting that the physics we discover in Earthbound laboratories applies throughout the observable cosmos. This universality extends to something even more fundamental: the constants of nature, the speed of light, the strength of gravity, the mass of electrons, dozens of numerical values that determine how matter and energy behave, all appear to be the same everywhere we look in space and time. This consistency makes the universe comprehensible to minds like ours, evolved on one small planet around one ordinary star. Yet this apparent fine-tuning raises profound questions. If any of these fundamental constants were even slightly different, stars might not form, atoms might not be stable, and complex chemistry might be impossible. The universe seems delicately balanced on a knife's edge between chaos and complexity, between simplicity and the intricate dance of forces that makes galaxies, planets, and life possible. As we continue our gentle exploration through cosmic mysteries, let's consider something that exists in almost unimaginable abundance throughout the universe, yet remains completely invisible to our eyes and instruments. Dark matter comprises roughly 85% of all matter in the cosmos, yet we can only detect it through its gravitational influence on visible matter. Imagine trying to understand a crowded dance floor while wearing a blindfold. You can hear the music and feel people bumping into you, but you can't see the dancers themselves. This is similar to how astronomers study dark matter. They can observe its gravitational effects on galaxies and galaxy clusters, but the mysterious substance itself refuses to interact with light in any detectable way. The evidence for dark matter is overwhelming and comes from multiple independent observations. Galaxies rotate too fast to hold themselves together with just the gravity from visible stars and gas. Galaxy clusters contain far more gravitational mass than we can account for with observable matter. The patterns of galaxy formation throughout cosmic history require additional unseen mass to explain how structure emerged from the smooth early universe. What makes dark matter even more intriguing is that it's not simply ordinary matter that happens to be dark. It appears to be composed of entirely unknown particles that interact with regular matter only through gravity. These hypothetical particles pass through ordinary atoms like ghosts, neither absorbing nor emitting electromagnetic radiation of any kind. Right now, billions of dark matter particles are likely streaming through your body every second without any noticeable effect. They're passing through the earth, through the walls of your room, through your skin and bones, completely undetected. You're immersed in an invisible ocean of exotic matter that makes up most of the universe's mass, yet remains as mysterious today as it was when first discovered decades ago. The search for dark matter has spawned some of the most sensitive physics experiments ever conceived. Deep underground, shielded from cosmic rays and other interference, scientists have built detectors capable of registering the incredibly rare occasions when a dark matter particle might collide with an ordinary atomic nucleus. So far, these experiments have detected nothing conclusive, adding to the mystery of what this dominant component of our universe actually is. Some theorists propose that dark matter consists of particles predicted by extensions to the standard model of particle physics. Others suggest more exotic possibilities, primordial black holes, extra dimensions, or even modifications to our understanding of gravity itself. The truth is, we simply don't know. And this ignorance about 85% of the universe's matter content represents one of the most humbling reminders of how much we still have to learn about cosmic reality. Paired with dark matter in cosmic abundance is an even more mysterious component called dark energy, which comprises roughly 68% of the universe's total energy density. While dark matter's gravity tends to pull things together, dark energy appears to be pushing space itself apart, causing the expansion of the universe to accelerate over time. This accelerating expansion was discovered accidentally in the late 1990s by astronomers studying distant supernovas. These stellar explosions are so bright they can be seen across billions of light years, and they all have very similar peak brightness, making them excellent cosmic distance markers. When astronomers measured how far away these supernovas were and how fast they were receding from us, they expected to find that the universe's expansion was slowing down due to gravity. Instead, they discovered that distant supernovas were fainter than expected, indicating they were farther away than predicted by models of a decelerating universe. The expansion of space itself was speeding up, driven by some unknown form of energy that permeates every cubic centimeter of seemingly empty space. This dark energy doesn't clump together like matter does. Instead, it appears to be smoothly distributed throughout space, maintaining constant density even as the universe expands. As space grows larger, more dark energy comes into existence, providing an ever-increasing push against gravity's tendency to slow cosmic expansion. The implications for the universe's future are profound. If dark energy continues to dominate, the expansion will accelerate indefinitely. Galaxies will drift apart until they're beyond each other's observable horizons. Star formation will gradually cease as gas and dust are diluted across ever larger volumes. Eventually, even the atoms themselves might be torn apart in a scenario cosmologists call the Big Rip. Yet despite decades of intensive research, we have no idea what dark energy actually is. It might be a property of space itself, a quantum field that fills the universe, or evidence that our understanding of gravity breaks down on cosmic scales. The most honest answer is that we're profoundly ignorant about the dominant component driving the universe's evolution. This cosmic humility is actually quite liberating. We live in a universe where 95% of everything that exists remains mysterious to us. We're explorers in the early stages of mapping a vast, largely unknown territory. Every observation potentially reveals new puzzles, every answer generates new questions, and the horizon of knowledge keeps expanding faster than we can approach it. As you settle deeper into this contemplation of cosmic mysteries, remember that this ignorance isn't a failure of human intelligence. It's a testament to the universe's infinite capacity for surprise, complexity, and wonder. We're conscious beings made of stellar debris, contemplating the very processes that created us, surrounded by dark oceans of the unknown. In this vast cosmic theatre of the unknown, let's turn our attention to something that might make you question the very nature of solid matter itself. The chair you're sitting in, the device you're listening to this on, even your own body, all of it is far more empty than solid. If you could somehow magnify an atom to the size of a football stadium, the nucleus would be smaller than a marble at the center, while the electrons would be tiny specks orbiting somewhere in the upper bleachers. This means that the matter we perceive as solid and substantial is actually composed of mostly empty space held together by invisible forces. The atoms in your hand and the atoms in the table beneath it never actually touch in the way we imagine. Instead, they're held apart by electromagnetic fields, like tiny magnets pushing against each other. The sensation of solid contact is really just the interaction of these force fields, creating the illusion of physical boundaries where none truly exist. What's even more remarkable is that these atomic components aren't really particles in the traditional sense at all. Electrons don't orbit atomic nuclei like planets around a sun. Instead, they exist as probability clouds, regions where they're likely to be found when observed. Before measurement, an electron exists in a state called superposition, simultaneously occupying multiple possible locations around the nucleus. This quantum behavior extends beyond individual atoms to influence the properties of matter on larger scales. The reason you can't push your hand through a solid wall isn't because the atoms are physically blocking each other like billiard balls. It's because the quantum mechanical properties of electrons create repulsive forces that prevent atoms from occupying the same space. In essence, the solid world around you is maintained by quantum uncertainty and electromagnetic fields rather than true physical substance. Moving from the quantum realm to the cosmic scale, let's explore one of the most beautiful examples of gravitational choreography in our solar system: the dance of Jupiter's moons. In 1610, when Galileo first pointed his telescope at Jupiter, he discovered 4 bright points of light that seemed to change position from night to night. These were the largest moons of Jupiter, now known as the Galilean satellites: Io, Europa, Ganymede, and Callisto. What Galileo witnessed was actually a complex gravitational ballet that has been playing out for billions of years. The innermost moon, Io, completes one orbit around Jupiter in just 42 hours. Europa takes twice as long, while Ganymede takes twice as long as Europa. This isn't coincidence, it's what astronomers call orbital resonance, where gravitational forces have locked these moons into precise mathematical relationships. This cosmic synchronization has profound consequences for these worlds. Io, caught in a gravitational tug-of-war between Jupiter and Europa, experiences such intense tidal forces that its interior remains molten. This makes Io the most volcanically active body in the solar system, with sulfur geysers erupting hundreds of miles into space, painting the moon's surface in brilliant yellows and oranges. Europa, the next moon outward, experiences similar but less intense tidal heating. This energy keeps a vast ocean of liquid water hidden beneath its icy surface, an ocean that may contain twice as much water as all of Earth's oceans combined. The gravitational stress creates cracks and ridges in Europa's ice shell, constantly renewing the surface and potentially allowing nutrients from the ocean below to reach space-based instruments. These tidal interactions demonstrate how gravity operates not just as a simple attractive force, but as a sculptor of worlds. The same gravitational dance that keeps Jupiter's moons locked in orbital resonance also shapes their geology, their potential for harboring life, and their evolution over cosmic time. It's a reminder that no celestial body exists in isolation. Each is part of a vast network of gravitational relationships that influence every aspect of its existence. Let's drift now towards something that challenges our intuitive understanding of temperature and energy. In the depths of space, far from any star, temperatures plunge to just a few degrees above absolute zero. This isn't simply very cold in the way we experience winter weather. It's a fundamental limit imposed by the laws of thermodynamics. Absolute zero, roughly negative 459 degrees Fahrenheit, represents the theoretical temperature at which all atomic motion would cease. At this point, particles would have no kinetic energy left to lose. Yet even in the coldest regions of interstellar space, temperatures rarely drop below about 2.7 degrees above absolute zero. This isn't because space is heated by distant stars, but because the entire universe is still slightly warm from its explosive beginning. The cosmic microwave background radiation, that faint afterglow of the Big Bang we discussed earlier, provides a minimum temperature floor for the entire universe. Every cubic centimeter of space, no matter how empty it appears, is bathed in this ancient light that has been stretched and cooled by cosmic expansion for nearly 14 billion years. Paradoxically, while the vacuum of space maintains this uniform cold temperature, objects in space can actually become much hotter than anything possible on Earth's surface. Without an atmosphere to carry heat away through convection, the only way objects in space can lose energy is through radiation. This means that spacecraft facing the sun can heat up to hundreds of degrees while their shadowed sides simultaneously freeze to temperatures far below anything experienced at Earth's poles. This extreme temperature variation presents unique challenges for space exploration. The James Webb Space Telescope, for instance, operates with one side facing the sun at over 180 degrees Fahrenheit, while its instruments are cooled to nearly absolute zero on the opposite side. This temperature difference of almost 500 degrees exists within the same structure, separated by just a few meters of specially designed insulation. These cosmic temperature extremes reveal something profound about energy and heat. Temperature isn't just a measure of how hot or cold something feels. It's a fundamental property related to the motion of particles and the flow of energy through space and time. In the vacuum between stars, individual particles might have tremendous kinetic energy, while the overall environment remains incredibly cold, simply because there are so few particles present to carry thermal energy. Now, let's explore something that connects the smallest scales of quantum mechanics to the largest structures in the observable universe. The phenomenon of cosmic inflation. In the first tiny fraction of a second after the Big Bang, space itself expanded faster than the speed of light, growing from smaller than a proton to larger than a grapefruit in less than a trillionth of a second. This isn't a violation of relativity's speed limit because nothing was actually moving through space faster than light. Instead, space itself was expanding, carrying matter and energy along with it like passengers on a cosmic escalator that was accelerating beyond light speed. This brief but dramatic period of inflation explains many of the large-scale properties of our universe that would otherwise seem impossible. Before inflation, different regions of what would become our observable universe were close enough together to reach thermal equilibrium, explaining why the cosmic microwave background radiation has such uniform temperature across the entire sky. The rapid expansion then stretched these regions far apart, preserving their thermal similarity across distances that light could never traverse in the universe's current age. Inflation also explains why space appears geometrically flat on large scales. Just as the surface of a balloon appears flat to an ant walking on it, the tremendous expansion of cosmic inflation stretched out any initial curvature in space-time, making our local region of the universe appear flat regardless of its original geometry. Perhaps most remarkably, quantum fluctuations during inflation became the seeds for all the large-scale structure we observe today. Tiny random variations in the density of matter and energy were stretched by inflation to cosmic proportions, eventually growing under gravity's influence to become the galaxies, galaxy clusters, and vast cosmic web that fills the universe today. This means that the Milky Way galaxy, our solar system, and ultimately our own existence can be traced back to random quantum events that occurred when the universe was smaller than an atomic nucleus. The galaxy clusters stretching across hundreds of millions of light years began as microscopic ripples in space-time, inflated to cosmic proportions in the universe's first moments. The evidence for inflation comes from incredibly precise measurements of the cosmic microwave background radiation, which show exactly the pattern of tiny temperature variations predicted by inflationary theory. These observations represent some of the most detailed confirmation of theoretical physics ever achieved, connecting quantum mechanics to cosmology across more than 60 orders of magnitude in scale. As we continue our gentle journey through cosmic revelations, let's contemplate something that makes our solar system's architecture seem almost impossibly precise: the orbital mechanics that govern planetary motion. The 8 planets of our solar system, along with countless asteroids, comets, and smaller bodies, all follow elliptical paths around the Sun with mathematical precision that has remained stable for billions of years. This cosmic clockwork operates according to laws discovered by Johannes Kepler over 4 centuries ago, refined by Newton's understanding of gravity, and perfected by Einstein's insights into the curvature of space-time. Each planet's orbital period is precisely determined by its distance from the Sun, following mathematical relationships so exact that we can predict planetary positions thousands of years into the future. Yet this apparent simplicity masks an underlying complexity that makes long-term orbital prediction one of the most challenging problems in physics. The gravitational influence of each planet affects all the others, creating a complex web of interactions that can only be calculated using powerful computers running for days or weeks to achieve high precision. Small perturbations in planetary orbits accumulate over time in ways that can fundamentally alter the solar system's configuration. Computer simulations suggest that Mercury's orbit is chaotic on timescales of millions of years, meaning tiny changes in its initial conditions could eventually lead to dramatically different outcomes, possibly even ejecting Mercury from the solar system or causing it to collide with Venus. This orbital chaos extends throughout the solar system, though with different characteristic timescales for different objects. The asteroid belt between Mars and Jupiter shows evidence of this gravitational chaos, with gaps in the distribution of asteroids corresponding to orbital periods that create resonances with Jupiter's motion. Over millions of years, asteroids in these resonant orbits are gradually ejected, creating the observed gaps. Even our Moon's orbit is slowly evolving due to tidal interactions with Earth. The same gravitational forces that create ocean tides are gradually slowing Earth's rotation and pushing the Moon farther away at a rate of about 1.5 inches per year. Billions of years ago, the Moon appeared much larger in the sky and Earth's day was significantly shorter, perhaps only 18 hours long. This orbital evolution means that the total solar eclipses we can witness today, where the Moon perfectly covers the Sun's disk, are a temporary cosmic coincidence. In the distant past, the Moon was too close and appeared too large to create the delicate corona effects we observe during eclipses. In the far future, the Moon will be too distant to completely cover the Sun, making total solar eclipses impossible. The clockwork precision of planetary orbits, combined with their underlying chaos and evolution, reveals something profound about the nature of cosmic order. The universe operates according to deterministic laws, yet those same laws can produce behavior so complex and sensitive to initial conditions that long-term prediction becomes impossible. We live in a cosmos that is simultaneously predictable and mysterious, ordered and chaotic, stable and constantly changing. These orbital mechanics extend far beyond our solar system to the billions of other planetary systems now being discovered around distant stars. The Kepler Space Telescope and other planet-hunting instruments have revealed an astonishing diversity of planetary architectures, many quite different from our own solar system's configuration. Some extrasolar systems contain hot Jupiters, massive planets orbiting extremely close to their stars with orbital periods of just a few days. Others have planets in highly elliptical orbits that take them from scorching proximity to their star to frozen distances farther than Pluto. Still others contain multiple planets locked in complex resonance chains, where the orbital periods form precise mathematical ratios maintained over billions of years. This diversity suggests that planetary system formation is a far more varied and complex process than we initially imagined. The architecture of our own solar system, with small rocky planets close to the Sun and large gas giants farther out, may be just one possible outcome among many, shaped by the particular conditions present in our region of the galaxy when the Sun and planets formed 4.5 billion years ago. As you let these cosmic revelations wash over you like a gentle tide, remember that you're not separate from these vast celestial mechanisms. The same gravitational forces that guide planets in their orbits also keep your feet planted on Earth's surface. The same nuclear processes that power distant stars also warm your skin when you step outside on a sunny day. The same quantum mechanical principles that govern the behavior of particles in deep space also determine the chemical reactions taking place in every cell of your body. You are intimately connected to this cosmic dance, a temporary arrangement of stellar debris that has somehow become conscious of its place in the vast symphony of space and time. Every breath you take contains atoms that have traveled through the cosmos for billions of years. Every heartbeat marks another moment in the ongoing story of a universe that continues to reveal new wonders to those patient enough to listen for its whispered secrets. As we drift deeper into our cosmic meditation, let's explore something that will transform how you think about the very fabric of reality itself. We've touched on how matter is mostly empty space, but now let's consider something even more fundamental: the nature of time itself and how it weaves through the universe in ways that would seem impossible if they weren't demonstrably true. Time, you see, isn't the steady, unchanging river flowing from past to future that we experience in our daily lives. Instead, it's more like a vast ocean with currents, eddies, and depths that vary depending on where you are and how fast you're moving. Right now, as you rest comfortably wherever you are, time is passing slightly differently for you than it is for someone standing just a few feet higher or lower than your current position. This isn't science fiction or philosophical speculation. It's measurable reality that affects the most mundane aspects of our technological world. The GPS satellites orbiting above us experience time at a slightly different rate than we do here on Earth's surface. They're moving fast enough and are far enough from Earth's gravitational well that their atomic clocks tick measurably faster than identical clocks on the ground. Without constantly correcting for these relativistic effects, your phone's navigation would accumulate errors of several miles within just a few hours. Every time you successfully find your way to a new restaurant or navigate through an unfamiliar city, you're benefiting from our understanding of how gravity and motion affect the flow of time itself. But the implications go far beyond practical applications. If you could somehow travel at speeds approaching that of light, you would experience one of the universe's most remarkable phenomena: time dilation. From your perspective aboard such a spacecraft, time would flow normally. You'd eat meals, sleep, read books, all at the usual pace. But relative to Earth, your biological processes, your thoughts, even the decay of radioactive elements in your body would slow dramatically. A journey that felt like a year to you might correspond to decades or even centuries passing on Earth. You could return from a voyage to a nearby star to find that everyone you knew had aged and died while you remained essentially unchanged. This isn't theoretical speculation, it's a direct consequence of how the universe actually works, confirmed by countless experiments with high-speed particles and atomic clocks. Even more remarkably, gravity has the same effect on time's passage. The stronger the gravitational field you're in, the slower time moves relative to regions with weaker gravity. This means that time passes slightly faster for your head than for your feet, though the difference is far too small to notice. Near a black hole, this effect becomes extreme. An astronaut falling toward the event horizon would appear to an outside observer to slow down and freeze. Their image stretched and redshifted until it faded from view. From the falling astronaut's perspective, however, time would continue flowing normally right up until they crossed the point of no return. This fundamental relativity of time challenges our deepest intuitions about the nature of existence and suggests that there's no universal now that applies everywhere in the cosmos simultaneously. Let's shift our contemplation now to something equally mind-bending: the quantum nature of reality at its most fundamental level. We've discussed how atoms are mostly empty space, but the behavior of particles at these tiny scales is far stranger than simple emptiness would suggest. In the quantum realm, the very concepts of definite position, momentum, and even existence become fuzzy and probabilistic. Consider a single electron orbiting the nucleus of an atom in your body right now. Classical physics would suggest this electron follows a definite path, like a tiny planet orbiting a miniature sun. But quantum mechanics reveals something far more mysterious. The electron doesn't have a definite location until something observes or measures it. Before observation, it exists as what physicists call a probability wave, spread out over multiple possible positions simultaneously. This isn't simply a limitation of our measuring instruments or a gap in our knowledge. It appears to be a fundamental feature of reality itself. The electron genuinely exists in multiple locations at once, in a state called superposition, until the act of observation forces it to choose a single position from among all the possibilities. What makes this even more extraordinary is that this quantum behavior isn't confined to isolated laboratory experiments. It's happening constantly throughout your body, in every atom of every cell, the chemical reactions that power your metabolism, the electrical signals in your nervous system, the very process by which your DNA replicates itself, all depend on quantum mechanical effects operating at scales far too small to perceive directly. The implications extend far beyond biology. Quantum mechanics suggests that reality at its most fundamental level is based on probability rather than certainty, on relationships between observations rather than independent facts about how things really are when no one is looking. This has led some physicists to propose that consciousness itself might play a fundamental role in determining what becomes real and what remains merely possible. Even more puzzling is the phenomenon of quantum entanglement, where particles become connected in ways that seem to defy our understanding of space and time. When two particles become entangled, measuring one instantly affects the other, regardless of ating them. This, the distant sepper-spooky action at a distance, as Einstein called it, has been confirmed in countless experiments, yet it continues to challenge our intuitive understanding of how information can travel through the universe. Some physicists suggest that entanglement might be the key to understanding how the universe maintains its coherence and why quantum effects don't simply cancel out when many particles interact. Others propose that entanglement creates a kind of cosmic web connecting every particle that has ever interacted, suggesting that the universe might be far more interconnected than it appears on the surface. As we continue our gentle drift through these cosmic mysteries, let's turn our attention to something that exists in almost unimaginable abundance, yet remains completely invisible: neutrinos. These ghostly particles are produced in vast quantities by nuclear reactions in stars, including our own trillions of neutrinos from Sun. Every second, trillions upon the Sun pass through every square centimeter of Earth's surface, including your body, without any noticeable effect. Neutrinos interact so weakly with ordinary matter that they can pass through entire planets as if nothing were there. A neutrino could travel through a wall of lead stretching from Earth to the nearest star and have only a 50-50 chance of interacting with a single atom along the way. They're produced not just by our Sun, but by every star in the galaxy, by cosmic ray interactions in the atmosphere, by radioactive decay in Earth's core, and by the residual heat of the Big Bang itself. What makes neutrinos particularly fascinating is that they carry information about processes and environments that are otherwise impossible to study. The neutrinos streaming from our Sun's core began their journey in the nuclear furnace, where hydrogen fuses into helium, providing direct evidence of the reactions that power our star. Unlike light, which can take hundreds of thousands of years to work its way from the Sun's core to its surface, neutrinos escape almost immediately, carrying fresh news about stellar fusion. Detecting these elusive particles requires some of the most sensitive instruments ever built, often housed deep underground to shield them from other forms of radiation. When scientists finally succeeded in observing solar neutrinos in the 1960s, they discovered something puzzling. There were only about 1/3 as many as theoretical models predicted. This solar neutrino problem persisted for decades until physicists realized that neutrinos could change their type or flavor as they traveled from the Sun to Earth. This discovery revealed that neutrinos have mass, albeit incredibly tiny amounts, and that they oscillate between different varieties during their journey through space. It was one of the first clear indications that the standard model of particle physics, while remarkably successful, was incomplete. Today, neutrino astronomy opens new windows onto cosmic phenomena, allowing us to study supernova explosions, black holes, and other extreme environments through their neutrino emissions. The fact that you're constantly immersed in this invisible sea of neutrinos, most of them having traveled across the galaxy or even from distant galaxies, connects you directly to nuclear processes occurring throughout the cosmos. Every second, neutrinos that began their journey in stellar cores billions of years ago are passing through your body, carrying information about conditions in long-dead stars and ancient cosmic events. Now let's explore something that demonstrates the universe's tendency toward both incredible violence and exquisite beauty: stellar death and rebirth. When massive stars exhaust their nuclear fuel, they don't simply fade away like a dying candle. Instead, they undergo one of the most catastrophic events in the universe: a core collapse supernova that can briefly outshine an entire galaxy containing hundreds of billions of stars. The process begins when a star at least 8 times more massive than our Sun runs out of nuclear fuel in its core. Without the outward pressure from fusion reactions to balance gravity's inward pull, the core collapses catastrophically. In less than a second, a region the size of Earth shrinks to a sphere only about 12 miles across while maintaining the mass of our entire Sun. This collapse generates temperatures and pressures so extreme that protons and electrons are crushed together to form neutrons, creating matter so dense that a teaspoon would weigh as much as Mount Everest. The infalling material rebounds off this incredibly dense core, sending a shockwave racing outward through the star at thousands of miles per second. When this shockwave reaches the star's surface, it tears the entire stellar envelope apart in an explosion so powerful it can be seen across billions of light years. The energy released in just 10 seconds exceeds what our Sun will produce over its entire 10 billion year lifetime. The explosion scatters the star's outer layers across light years of space, enriching the interstellar medium with heavy elements forged in the stellar core and during the explosion itself. But perhaps the most remarkable aspect of these cosmic detonations is what they leave behind. If the original star was massive enough, the collapsed core becomes a black hole, a region of space-time so warped that nothing, not even light, can escape once it crosses the event horizon. Less massive cores become neutron stars, city-sized objects containing more mass than our Sun, spinning at rates of hundreds of times per second while generating magnetic fields trillions of times stronger than Earth's. These neutron stars are among the most exotic objects in the universe, with properties that push physics to its absolute limits. Their surfaces are so smooth that the largest irregularities would be only millimeters high, yet they're simultaneously so magnetic that atoms near the surface are stretched into needle-like shapes. Some neutron stars emit beams of radiation from their magnetic poles, creating cosmic lighthouses called pulsars that sweep across space with clockwork precision. The gravitational waves detected by Earth-based instruments often originate from neutron star mergers, collisions so violent they can be felt as space-time ripples across billions of light-years. These cosmic crashes create conditions even more extreme than supernova explosions, forging the heaviest elements in the universe, including gold, platinum, and uranium. The gold in any jewelry you might own was likely created in such a collision billions of years ago, then scattered through space to eventually become part of the gas cloud that formed our solar system. This cycle of stellar death and rebirth has been operating for over 13 billion years, with each generation of stars building on the chemical legacy of their predecessors. Our Sun is at least a third-generation star, formed from material enriched by countless earlier stellar deaths. Without those ancient supernovas, there would be no rocky planets, no complex chemistry, and no life as we know it. As we near the midpoint of our cosmic journey tonight, let's pause to contemplate something that brings together many of the themes we've explored. The remarkable fine-tuning of physical constants that makes our universe capable of supporting complexity, structure, and ultimately life itself. The fundamental forces of nature, the masses of particles, the rate of cosmic expansion all appear to be precisely balanced in ways that allow stars to form, atoms to remain stable, and chemistry to produce the complex molecules necessary for biological processes. Consider gravity, the weakest of the fundamental forces, yet crucial for building cosmic structure. If gravity were slightly stronger, stars would form more easily, but burn out much faster, potentially preventing the billions of years of stable stellar evolution necessary for life to emerge. If it were weaker, matter might never clump together enough to form stars and galaxies at all, leaving the universe as a thin, cold soup of particles. The electromagnetic force that binds atoms together also appears fine-tuned with remarkable precision. If it were slightly stronger, electrons would be pulled so tightly to atomic nuclei that chemical bonding would become impossible. If it were weaker, atoms couldn't hold themselves together, and matter as we know it wouldn't exist. Even more remarkably, the rate of cosmic expansion seems perfectly calibrated to allow structure formation. If the universe had expanded too quickly after the Big Bang, matter would have been diluted before gravity could pull it together into stars and galaxies. If expansion had been too slow, the universe might have collapsed back on itself before stars had time to form and evolve. The nuclear forces that govern fusion reactions in stellar cores also appear precisely tuned. Small changes in these forces would alter the nuclear physics of stars, potentially preventing the formation of carbon, oxygen, and other elements essential for life. The fact that carbon can form at all in stellar cores depends on a remarkable coincidence in energy levels that allows 3 helium nuclei to combine in a process that would otherwise be impossibly improbable. This apparent fine-tuning raises profound questions about the nature of our universe and our place within it. Some physicists propose that we live in a multiverse containing countless universes with different physical constants, and we naturally find ourselves in one of the rare universes where the constants happen to allow complexity and life to emerge. Others suggest that the constants might not be as finely tuned as they appear, that there could be multiple ways for complexity to arise even with different physical laws. Still others see the fine-tuning as evidence for deeper principles we don't yet understand, mathematical relationships that constrain the possible values of physical constants in ways we haven't discovered. What remains clear is that we exist in a universe that seems almost impossibly well suited for the emergence of stars, planets, chemistry, and consciousness. Whether this is the result of cosmic coincidence, deeper physical principles, or selection effects in a vast multiverse, it represents one of the most profound mysteries in all of science. As you continue to rest in this contemplation of cosmic wonders, remember that you are both a product of this fine-tuned universe and one of the ways it has come to understand itself. The atoms in your body were forged in stellar cores. The forces that govern your biological processes are the same ones that shape galaxies. And your consciousness represents the cosmos becoming aware of its own remarkable properties and evolution. Each breath you take connects you to the nuclear fusion reactions powering stars across the galaxy. Each thought you think engages quantum processes that operate according to the same mysterious principles governing particle behavior throughout the universe. You are not separate from these cosmic forces and phenomena, but rather a temporary, beautiful expression of the universe's ongoing experiment in complexity, consciousness, and wonder. In the gentle rhythm of your breathing, in the steady beating of your heart, in the quiet electrical activity of your brain as you process these ideas. The same fundamental forces that sculpt galaxies and guide the evolution of stars are playing out on the intimate scale of your own existence. You are the universe dreaming about itself, matter organized in such a way that it can contemplate the very processes that brought it into being. As we drift deeper into our cosmic reverie, let's explore something that will make you question the very nature of solid matter and the ground beneath your feet. You see, the Earth you're resting upon right now isn't the stable, unchanging foundation it appears to be. Instead, you're actually riding on the surface of a dynamic, living planet that's constantly reshaping itself through processes so gradual they're invisible to human perception, yet so powerful they can move entire continents across the globe. Deep beneath your feet, roughly 1,800 miles down, lies a layer of our planet that exists in a state unlike anything we experience at the surface. The Earth's mantle, comprising about 84% of our planet's volume, consists of rock so hot it flows like thick honey, driven by temperature differences between the scorching core and the relatively cool surface. This isn't molten rock in the way we might imagine lava, but rather solid material heated to such extreme temperatures that it becomes plastic, capable of flowing over geological timescales. These slow-motion currents in the mantle drive one of the most remarkable processes on Earth: plate tectonics. The solid ground beneath you is actually part of a massive puzzle piece, one of roughly 15 major tectonic plates that fit together like a spherical jigsaw puzzle covering our planet's surface. These plates are constantly in motion, drifting at rates of just a few centimeters per year, about the same speed your fingernails grow. Yet this seemingly imperceptible movement has profound consequences over millions of years. The Atlantic Ocean is gradually widening as new seafloor is created along the mid-Atlantic ridge, pushing Europe and North America farther apart year by year. Meanwhile, the Pacific Ocean is slowly shrinking as its edges are consumed in deep ocean trenches where oceanic plates dive beneath continental ones. This planetary recycling system means that the oldest rocks on Earth's surface are only about 4 billion years old, despite our planet being 4.5 billion years old. The rest has been consumed and reformed countless times through the endless dance of creation and destruction that characterizes our geologically active world. The evidence of this planetary dynamism surrounds us if we know how to look for it. The Himalayan mountains, those towering peaks that seem so permanent and ancient, are actually among Earth's youngest mountain ranges, formed when the Indian subcontinent crashed into Asia roughly 50 million years ago. This collision continues today, pushing the mountains higher at a rate of several millimeters per year, even as erosion wears them down. Similarly, the beautiful symmetry of the Atlantic Ocean's coastlines isn't coincidental. If you were to slide South America and Africa together like puzzle pieces, they would fit almost perfectly, revealing their common origin as parts of the ancient supercontinent Pangaea. This continental drift continues today, with GPS measurements showing that locations in Europe and North America are separating at about the same rate that human hair grows. These massive geological processes connect to something even more fundamental about our planet's relationship with the cosmos. Earth's magnetic field, generated by the motion of molten iron in our planet's core, creates an invisible shield that protects us from the constant stream of charged particles flowing from the sun. Without this magnetic protection, our atmosphere would gradually be stripped away by the solar wind, leaving Earth as barren as Mars. The strength and orientation of this magnetic field isn't constant either. Throughout Earth's history, the magnetic poles have reversed hundreds of times, with north becoming south and south becoming north. These reversals, recorded in the magnetic minerals of ancient rocks, provide a timeline of our planet's magnetic evolution and help scientists understand the complex dynamics occurring deep within Earth's interior. Even more remarkably, Earth's magnetic field appears to be weakening currently, declining by about 5% per century. Some scientists suggest we might be approaching another magnetic reversal, though the process typically takes thousands of years to complete. During such transitions, our planet's magnetic protection becomes temporarily weakened, potentially affecting everything from satellite communications to animal navigation systems that rely on magnetic field detection. As we continue our gentle exploration through cosmic mysteries, let's turn our attention to something that demonstrates the universe's capacity for creating order from chaos on the grandest possible scales. The cosmic web, a vast network of dark matter filaments that connects galaxies across billions of light years, creating the largest structures in the known universe. If you could somehow step outside our observable universe and look back at it, you wouldn't see galaxies scattered randomly through space like stars sprinkled across a dark sky. Instead, you would observe an intricate web-like pattern, with galaxies strung along filaments of dark matter like dewdrops on a spider's web. These cosmic filaments, some stretching for hundreds of millions of light years, are separated by vast voids containing almost no matter at all. This cosmic web represents the universe's largest scale architecture, formed by the same gravitational forces that keep planets in orbit around stars and stars in orbit around galactic centers. Over billions of years, gravity has amplified tiny density fluctuations that existed in the early universe, gradually pulling matter together along preferred directions to create this magnificent cosmic scaffolding. The voids between these filaments aren't truly empty, but they contain so little matter that a typical void might have only 1 atom per cubic meter of space. To put this in perspective, the air you're breathing contains roughly 25 trillion atoms per cubic meter. These cosmic voids are among the emptiest regions in the universe, vast territories of space where a traveler could journey for millions of light years without encountering a single galaxy. Yet even in these apparently barren regions, dark energy continues its mysterious work, causing space itself to expand and pushing the cosmic web's components ever farther apart. This expansion doesn't just increase the distances between galaxies, it actively creates new space, diluting the already sparse matter in cosmic voids to even lower densities. The cosmic web also serves as a highway system for intergalactic material. Gas flows along the dark matter filaments, feeding star formation in galaxies and enabling the chemical evolution that enriches the universe with heavy elements. When massive stars explode as supernovas, they can eject material that travels along these cosmic pathways, seeding distant regions with the elements necessary for planet formation and life. This vast cosmic infrastructure influences the evolution of galaxies in profound ways. Galaxies located at the intersections of multiple filaments in regions cosmologists call clusters experience frequent gravitational interactions that can trigger bursts of star formation or strip gas from smaller galaxies entirely. Meanwhile, galaxies in the cosmic voids evolve in relative isolation, maintaining their star-forming capabilities over longer periods. The discovery of the cosmic web's detailed structure represents one of the great triumphs of modern astronomy, achieved through surveys that map the positions of millions of galaxies across vast volumes of space. These three-dimensional maps reveal patterns that match remarkably well with computer simulations of cosmic evolution, providing strong confirmation of our understanding of how the universe grew from smooth initial conditions to the complex structure we observe today. Let's drift now towards something that brings the cosmic web down to a more personal scale. The journey that every atom in your body has taken through this vast cosmic architecture. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it has traveled along the cosmic web's pathways, carried by stellar winds, supernova explosions, and the gradual flow of intergalactic gas. These atoms began their cosmic odyssey in the nuclear furnaces of massive stars, many of which lived and died when the universe was much younger and smaller than it is today. When these ancient stars exploded, they scattered their heavy elements into the surrounding space, where the material joined the slow migration of gas along dark matter filaments toward regions where new stars and planetary systems could form. Some of the atoms in your body may have spent millions of years drifting through the cosmic voids, part of tenuous gas clouds moving at speeds of hundreds of kilometers per second toward distant galaxies. Others might have been recycled multiple times through different stellar generations, forged initially in one star, dispersed by its death, then incorporated into new stars where they underwent additional nuclear processing before being expelled again. This cosmic recycling program operates on timescales that dwarf human experience, yet it connects every living thing on Earth to the largest structures in the universe. The carbon atoms that form the backbone of every protein in your body, the phosphorus atoms in your DNA, the trace metals that enable crucial biological processes, all have traveled billions of light years through the cosmic web to arrive at precisely the right place and time to become part of you. Even more remarkably, this process continues today. Every breath you take contains atoms that have recently completed epic journeys through interstellar space. Some may have been expelled from dying stars in our own galaxy, while others could have originated in distant galaxies and traveled for billions of years along cosmic web filaments before eventually reaching Earth's atmosphere. This perspective transforms our understanding of what it means to be human. You aren't separate from the cosmic web. You are a temporary concentration of material that has flowed through its vast networks for eons. Your existence represents a brief moment when atoms that have wandered the universe for billions of years have come together in just the right configuration to create consciousness, awareness, and the capacity to contemplate the very cosmic processes that created you. As we continue our tranquil voyage through space's wonders, let's explore something that demonstrates how the universe creates beauty through the interplay of fundamental forces, the formation and evolution of planetary rings. These delicate structures, most famously displayed by Saturn but present around all four gas giants in our solar system, represent some of the most elegant examples of celestial mechanics in action. Saturn's rings, visible through even modest telescopes as a brilliant band of light encircling the planet, consist of countless individual particles ranging in size from tiny ice crystals to house-sized boulders. Each of these particles follows its own independent orbit around Saturn, yet together they create structures of breathtaking beauty and mathematical precision. The rings aren't solid disks despite their appearance from Earth. Instead, they're more like vast traffic patterns, with billions of particles moving at different speeds depending on their distance from Saturn. Inner particles orbit faster than outer ones, following the same gravitational laws that govern planetary motion around the Sun. This differential motion creates the intricate patterns and divisions we observe, including gaps where gravitational resonances with Saturn's moons prevent particles from maintaining stable orbits. What makes Saturn's rings particularly spectacular is their composition and youth. Unlike the ancient rocky material that forms many celestial bodies, Saturn's rings consist primarily of water ice, giving them a brilliant reflectivity that makes them visible across the solar system. This icy composition suggests the rings are relatively young in astronomical terms, perhaps only a few 100 million years old, formed when a large moon or comet wandered too close to Saturn and was torn apart by tidal forces. The process that creates and maintains these ring systems reveals something profound about how gravity operates on different scales. The same tidal forces that raise ocean waters on Earth become destructive when applied to larger bodies approaching massive planets. Any object that ventures within a planet's Roche limit, the distance where tidal forces overcome the object's own gravity, will be gradually pulled apart and distributed into a ring system. This destruction isn't violent or sudden like a collision. Instead, it's a gradual process where the side of the approaching object closest to the planet experiences stronger gravity than the far side. Over time, this differential pull stretches the object until it can no longer hold itself together, creating a stream of debris that eventually spreads around the planet's equator. Jupiter's rings, though much fainter than Saturn's, tell a different story of cosmic bombardment and renewal. These thin, dusty rings are constantly replenished by meteoroid impacts on Jupiter's small inner moons. Each impact blasts tiny particles into space, where they're captured by Jupiter's gravity and spread into ring-like patterns. Without this constant resupply, Jupiter's rings would disappear within decades, swept away by radiation pressure and gravitational perturbations. The rings of Uranus and Neptune, discovered only in recent decades, reveal yet another mechanism for ring formation and evolution. These narrow, dense rings appear to be confined by small shepherd moons that orbit just inside and outside each ring, using their gravity to prevent the ring particles from spreading outward or falling inward toward the planet. These shepherd moons create a delicate gravitational dance where any particle that strays too far from its designated ring location is gently nudged back into place. This process requires exquisite precision. The moons must be exactly the right size and in exactly the right orbits to maintain the ring's narrow, well-defined structure. The study of planetary rings has revealed that these systems are far more dynamic and ephemeral than early astronomers imagined. Computer simulations suggest that ring systems form, evolve, and dissipate on timescales of millions to billions of years. The magnificent rings we observe today may be temporary phenomena, destined to either fall into their parent planets or be dispersed into space as their particles gradually lose energy through countless tiny collisions. This transient nature makes us remarkably fortunate to live at a time when Saturn's rings are at their most spectacular. In the distant future, they may fade to thin, barely visible wisps or disappear entirely, leaving only historical records and scientific measurements to document their former glory. We are witnesses to one of the universe's most beautiful accidents, a cosmic sculpture created by gravity and maintained by the delicate balance of forces operating across millions of cubic kilometers of space. Moving from the elegance of ring systems to something even more fundamental, let's explore how the universe has evolved from the smooth, nearly uniform conditions of the early cosmos to the complex, structured reality we observe today. This transformation represents one of the most remarkable aspects of cosmic evolution. The gradual emergence of complexity from simplicity through the patient work of gravity and time. In the universe's earliest moments, matter was distributed almost perfectly uniformly throughout space. The cosmic microwave background radiation shows us a snapshot of this ancient era, revealing temperature variations of only a few parts in 100,000 across the entire sky. Yet these tiny ripples, barely perceptible against the cosmic background, contain the seeds of every galaxy, star, and planet that would eventually form. Over millions of years, gravity began amplifying these microscopic density differences. Regions where even that slightly denser than their surroundings attract growing more matter, gradually larger and denser still. This process of gravitational amplification worked like compound interest, with small advantages accumulating over time into dramatic differences in density. The first structures to condense out of this cosmic soup were dark matter halos, invisible scaffolding that provided the gravitational framework for galaxy formation. These dark matter concentrations drew in ordinary matter, heating it through gravitational compression until it began glowing with the light of the universe's first stars. These primordial stars were fundamentally different from the Sun and other stars we see today. Formed from gas containing only hydrogen and helium, they grew to enormous sizes and burned with incredible intensity, exhausting their nuclear fuel in just a few million years before exploding as some of the most powerful supernovas in cosmic history. When these first-generation stars died, they scattered the heavy elements they had created through nuclear fusion into the surrounding space, enriching the cosmic gas with carbon, oxygen, silicon, iron, and dozens of other elements. This chemical enrichment made possible the formation of second-generation stars, rocky planets, and eventually the complex chemistry necessary for life. The process of cosmic structure formation continues today, though at a much slower pace than in the universe's youth. Galaxy clusters are still growing through mergers and accretion, dark matter halos are still capturing additional material, and new stars are still forming in gas clouds enriched by billions of years of stellar evolution. Yet this gradual construction of cosmic complexity operates against the backdrop of accelerating expansion driven by dark energy. While gravity works to pull matter together into increasingly dense structures, dark energy pushes space itself apart, fighting against gravitational collapse on the largest scales. This cosmic tension between gravity's tendency to create structure and dark energy's drive toward expansion will ultimately determine the universe's fate. Current observations suggest that dark energy will win this battle, leading to a future where galaxies become increasingly isolated as the space between them grows ever larger. In this far future cosmos, star formation will gradually cease as gas becomes too dilute to collapse into new stars. Existing stars will exhaust their fuel and fade away, leaving behind white dwarfs, neutron stars, and black holes as the only remnants of today's vibrant stellar populations. Eventually, even these compact objects may decay or evaporate, leaving the universe as a cold, empty expanse populated only by elementary particles and the quantum fluctuations of empty space. Yet this distant future, trillions upon trillions of years away, doesn't diminish the significance of our current cosmic moment. We exist during what might be called the universe's golden age, when stars shine brightly, galaxies dance together in cosmic clusters, and the conditions exist for complexity, chemistry, and consciousness to flourish. The atoms in your body, forged in stellar cores and scattered by supernovas, represent temporary arrangements of matter that have achieved the remarkable feat of self-awareness during this brief window of cosmic fertility. You are the universe's way of experiencing its own beauty and complexity during the relatively short epoch when such experiences are possible. As you rest here, contemplating these vast scales of space and time, remember that your existence bridges the gap between the quantum realm and the cosmic web, between the first moments after the Big Bang and the distant future when stars will cease to shine. You are both infinitesimal and central, temporary and eternal, a conscious witness to the universe's ongoing experiment in creating order, beauty, and meaning from the fundamental forces that shape reality itself. In the gentle rhythm of your breathing, the steady circulation of blood carrying stellar iron through your veins, the electrical patterns in your brain as you process these cosmic concepts, the same forces that sculpted galaxies and ignited the first stars continue their ancient work on the intimate scale of your biological existence. You are not merely observing the universe, you are the universe observing itself. Matter organized in such a way that it can contemplate the very processes that brought it into being across 13.8 billion years of cosmic evolution. As we drift deeper into our cosmic meditation, let's turn our attention to something that will transform how you think about the very nature of light itself. You see, light isn't simply the illumination that fills your room, or the starshine that filters through your window. It's actually one of the most mysterious and fundamental aspects of reality, carrying information across the universe at a speed so precise it defines our very understanding of space and time. Every photon of light that reaches your eyes has traveled at exactly the same speed through the vacuum of space, roughly 300 million meters per second. This isn't just impressively fast, it represents a cosmic speed limit built into the fabric of the universe itself. Nothing with mass can ever reach this velocity, yet light, being massless, has no choice but to travel at this exact pace through empty space. What makes this even more remarkable is that light's journey through the cosmos reveals the history of everything we can observe. When you gaze up at the night sky, you're not seeing the stars as they are now, but as they were when their light began its long voyage toward Earth. The nearest star beyond our sun appears to you as it existed over 4 years ago. More distant stars show themselves as they were decades, centuries, or even millennia in the past. This temporal layering means that every glance upward is actually a form of time travel, using light as your vehicle to peer into the cosmic past. The faint glow of the Andromeda galaxy carries information from 2.5 million years ago, when our earliest human ancestors were just learning to fashion the first stone tools. Even more ancient light streams toward us from galaxies so distant that we see them as they appeared when the universe was young and stars were first beginning to shine. But light doesn't just travel through space unchanged. As the universe expands, it stretches the wavelengths of photons crossing vast cosmic distances, shifting their colors toward the red end of the spectrum. This redshift effect allows astronomers to measure how fast distant galaxies are moving away from us, revealing that space itself is expanding and carrying those galaxies along with it. The implications are profound. The universe isn't just getting bigger, it's growing at an accelerating rate, driven by the mysterious force we call dark energy. This cosmic acceleration means that galaxies beyond a certain distance are receding from us faster than their light can travel toward us, creating a horizon beyond which we can never see, no matter how long we wait or how powerful our telescopes become. This cosmic horizon doesn't represent an edge or boundary in space itself, but rather a limit imposed by the finite age of the universe and the constant speed of light. Beyond this invisible boundary, there may be countless more galaxies, stars, and perhaps even other forms of life, but their light will never reach us because space is expanding too rapidly between us. Moving from the cosmic scale to something more intimate, let's explore how light interacts with matter in ways that make vision and color possible. The light that illuminates your surroundings right now is constantly interacting with every surface, every object, every particle of dust in the air around you. When photons strike an object, some are absorbed while others are reflected, and it's these reflected photons that carry information about color, texture, and form to your eyes. The colors you perceive aren't inherent properties of objects themselves, but rather the specific wavelengths of light that those objects reflect. A red rose appears red because its petals absorb most wavelengths of visible light, while reflecting primarily those that correspond to red. The blue sky overhead results from sunlight being scattered by tiny particles and molecules in Earth's atmosphere, with shorter blue wavelengths being scattered more effectively than longer red ones. This interaction between light and matter operates according to quantum mechanical principles that govern how electrons in atoms respond to electromagnetic radiation. When a photon strikes an atom, it can boost an electron to a higher energy level, but only if the photon carries exactly the right amount of energy. This quantized absorption creates the distinctive spectral lines that allow astronomers to identify elements in distant stars and galaxies. The same quantum processes that create these spectral fingerprints also power the nuclear fusion reactions in stellar cores. Deep within stars, hydrogen nuclei overcome their mutual electrical form helium, releasing tremendous amounts of repulsion and fuse together to energy in the process. This energy works its way gradually outward through the star's interior, eventually reaching the surface and streaming into space as the light that illuminates planets and enables photosynthesis on worlds capable of supporting life. In our own solar system, the Sun converts over 4 million tons of matter into pure energy every second through nuclear fusion, following Einstein's famous equation that relates mass and energy. This continuous transformation has been powering our star for nearly 5 billion years and will continue for roughly another 5 billion years before the Sun exhausts its hydrogen fuel and begins the next phase of stellar evolution. The light from our Sun takes just over 8 minutes to travel the 93 million miles to Earth, but the energy that creates that light began its journey in the solar core hundreds of thousands of years earlier. Photons produced by fusion reactions must work their way through the dense stellar interior, being absorbed and re-emitted countless times before finally reaching the surface and escaping into space. This means that the sunlight warming your face right now began as nuclear energy deep within our star when human civilization was in its earliest stages. The photons that enable you to see these words have been on an epic journey through time and space, carrying energy that was locked within atomic nuclei until fusion reactions set it free to illuminate the cosmos. Let's drift now towards something that reveals the universe's capacity for creating the most extreme environments imaginable. Neutron stars, the collapsed cores of massive stars that have undergone supernova explosions. These city-sized objects contain more mass than our entire sun compressed into a sphere only about 12 miles across, creating matter so dense that a single teaspoon would weigh as much as Mount Everest. The formation of a neutron star requires conditions so extreme they push the laws of physics to their absolute limits. When a massive star exhausts its nuclear fuel, gravity overwhelms all other forces and crushes the stellar core with such violence that protons and electrons are squeezed together to form neutrons. The resulting object is essentially a gigantic atomic nucleus held together by neutron degeneracy pressure and strong nuclear forces. The surface of a neutron star presents an environment utterly alien to anything we experience on Earth. Gravity is so intense that escape velocity approaches half the speed of light, meaning that any object dropped from just 1 meter above the surface would impact with the energy of a nuclear bomb. The magnetic field strength can exceed Earth's by factors of trillions, creating conditions where atoms are stretched into needle-like shapes and the vacuum itself becomes polarized. Many neutron stars rotate rapidly, some spinning hundreds of times per second while maintaining their spherical shape through the incredible strength of neutron degeneracy pressure. These rotating magnetic lighthouses, called pulsars, emit beams of radiation from their magnetic poles that sweep across space like cosmic searchlights. When these beams point toward Earth, we detect regular pulses of radio waves arriving with clockwork precision. The regularity of pulsar signals is so extraordinary that they were initially mistaken for possible alien communications when first discovered in the 1960s. Some pulsars keep time more accurately than the best atomic clocks on Earth, slowing down by only seconds over millions of years as they gradually lose rotational energy through electromagnetic radiation. When two neutron stars orbit each other and eventually spiral inward due to gravitational wave emission, their collision creates one of the most violent events in the universe. These neutron star mergers generate gravitational waves that ripple across space-time at the speed of light, carrying information about the collision to gravitational wave detectors on Earth and beyond. The collision itself lasts only milliseconds, but it releases more energy than our sun will produce over its entire lifetime. The extreme conditions during the merger create elements heavier than iron through rapid neutron capture processes, forging gold, platinum, uranium, and other heavy elements that cannot be produced in ordinary stellar cores. Much of the gold in Earth's crust and in any jewelry you might own was likely created during such neutron star collisions billions of years ago, then scattered through space and incorporated into the gas clouds that eventually formed our solar system. Every gold atom has survived an incredibly violent cosmic event and traveled vast distances through space and time to become part of our planet. The gravitational waves produced by these mergers carry information about the fundamental nature of space-time itself. When they wash over Earth, they stretch and compress space by distances smaller than 1/10,000th the width of a proton. Yet our instruments can detect these minute distortions and use them to study cosmic events occurring billions of light-years away. This gravitational wave astronomy opens entirely new windows onto the universe, allowing us to observe phenomena that produce no electromagnetic radiation. Black hole mergers, neutron star collisions, and potentially even the rapid expansion of space during cosmic inflation all generate gravitational waves that carry unique information about processes we could never study through traditional telescope observations. As we continue our gentle voyage through cosmic wonders, let's explore something that demonstrates how the universe creates order and beauty through the interplay of fundamental forces on the grandest scales: galaxy formation and evolution. The magnificent spiral and elliptical galaxies we observe today grew from tiny density fluctuations in the early universe, shaped by billions of years of gravitational attraction, stellar birth and death, and the mysterious influence of dark matter. In the universe's youth, when it was only a few 100 million years old, the first galaxies were small, irregular collections of young, hot stars burning through their nuclear fuel at prodigious rates. These primordial galaxies contained no heavy elements beyond hydrogen and helium, limiting their ability to form rocky planets or complex chemistry. Yet they played a crucial role in cosmic evolution by creating and dispersing the first heavy elements through supernova explosions. Over billions of years, smaller galaxies merged together under gravity's influence, building larger and more complex structures. Our own Milky Way galaxy has grown through countless such mergers, and evidence of this violent past can still be seen in the streams of stars that mark the disrupted remains of smaller galaxies that wandered too close to our galactic neighborhood. The spiral arms that give galaxies like the Milky Way their distinctive appearance aren't fixed structures rotating like solid wheels. Instead, they're density waves that sweep around the galactic disk, triggering star formation as they compress interstellar gas clouds. Stars form within these spiral arms, but their individual orbits carry them in and out of the arms over millions of years, creating the illusion of permanent spiral structure while the changes. At actual stellar content constantly, the center of nearly every large galaxy lies a supermassive black hole containing millions or billions of times the mass of our Sun. These cosmic monsters grow by accreting material from their surroundings and through mergers with other black holes when galaxies collide. The relationship between central black holes and their host galaxies appears to be fundamental to galactic evolution, with this mass closely black hole correlated to the properties of the surrounding stellar bulge. When supermassive black holes actively feed on surrounding material, they can outshine entire galaxies, creating the brilliant quasars visible across billions of light years. The energy released by matter falling into these black holes can drive powerful jets of particles at near light speeds, extending far beyond the galaxy and affecting star formation throughout the surrounding cosmic environment. Our local group of galaxies, including the Milky Way and the Andromeda Galaxy, is slowly being pulled toward a much larger structure called the Virgo cluster, which contains over 1,000 galaxies bound together by their mutual gravitational attraction. This cluster, in turn, is part of an even larger structure called the Laniakea supercluster, spanning over 500 million light-years and containing the mass of 100,000 trillion suns. The motion of our entire local galactic neighborhood toward the Virgo cluster means that we're participating in cosmic flows that operate on scales far larger than individual galaxies. These bulk motions reflect the universe's large-scale structure and the distribution of dark matter that provides the gravitational framework for cosmic architecture. Yet even as we participate in these vast cosmic flows, the expansion of space driven by dark energy is gradually winning the battle against gravity on the largest scales. Galaxy clusters separated by more than a few 100 million light-years are being carried apart by cosmic expansion faster than their mutual gravity can pull them together, creating an increasingly isolated island universe of gravitationally bound structures. In approximately 4.5 billion years, our Milky Way will collide and merge with the Andromeda Galaxy in a cosmic dance that will fundamentally reshape both galaxies. Computer simulations suggest this merger will trigger intense bursts of star formation while flinging some stellar systems into intergalactic space. The resulting elliptical galaxy, sometimes nicknamed Milkomeda, will represent a new chapter in our cosmic neighborhood's evolution. This galactic merger will occur roughly the same time that our Sun begins its own evolutionary transformation into a red giant star, swelling to enormous size as it exhausts the hydrogen fuel in its core. The coincidental timing of these events represents just one example of how cosmic processes operate on multiple scales simultaneously, from stellar evolution to galactic dynamics. As we near the final portion of our cosmic journey tonight, let's contemplate something that brings together all the themes we've explored: the remarkable emergence of complexity from simplicity that has characterized the universe's evolution from its earliest moments to the present day. This ongoing transformation from smooth initial conditions to the rich tapestry of structure and phenomena we observe today represents one of the most profound aspects of cosmic history. The universe began in a state of almost perfect uniformity, with matter and energy distributed nearly evenly throughout space. Yet tiny quantum fluctuations, variations so small they existed only as probability waves in the early cosmic soup, contained within them the seeds of every galaxy, star, and planet that would eventually form. Through the patient work of gravity operating over billions of years, these microscopic irregularities grew into the magnificent cosmic web of filaments and voids that spans the observable universe today. The same fundamental forces that govern the falling of an apple from a tree have sculpted the largest structures in existence, demonstrating the profound unity underlying all physical phenomena. This cosmic evolution continues today, though at a pace far slower than during the universe's tumultuous youth. New stars are still being born in stellar nurseries where gravity compresses gas clouds to the point where nuclear fusion ignites. Planetary systems continue forming around these young stars, potentially creating new worlds where the chemistry of life might someday take hold. Yet this construction of complexity operates against the backdrop of universal expansion and the mysterious influence of dark energy. While gravity works to create structure and concentrate matter into stars, planets, and living systems, dark energy drives space itself apart, gradually diluting the universe and making future structure formation increasingly difficult. As we reach the end of our gentle journey through the cosmos, remember that you carry within yourself the entire story of the universe. From quantum fluctuations to galactic collisions, from stellar nucleosynthesis to the expansion of space-time itself, you are both observer and participant in this magnificent cosmic dance. Rest well, knowing you're made of stardust, surrounded by wonders beyond imagination, forever connected to the infinite tapestry of space and time. Sweet dreams, fellow cosmic wanderer, and time. Sweet dreams, fellow cosmic wanderer.